Next is number 51, chapter 15, problem 51. And we're given a spherical shell that's conducting, and we're given a charge inside that shell of positive Q. Outside the shell has a charge of negative Q. So this shell has negative Q, and then there's positive Q inside. We want to find the E field, the electric field, outside and inside the shell. So we need to use Gauss's law. So the first one, outside, is actually pretty easy for this problem, because Gauss's law is going to give you 4 pi r squared E times E is equal to the charge enclosed, total charge enclosed, over epsilon naught. So we need to draw a Gaussian surface. So this is just some surface that we can kind of draw around the whole scenario, right? So now we take total charge enclosed is going to be negative Q plus positive Q. So let's take those. 1 over epsilon naught, negative Q plus Q is equal to 0. So the charge outside, or the electric field outside, is going to be 0. Because what we do typically is we take this, then we take these things to the other side, 4 pi r squared, but still Q enclosed in this case is 0. So that equals 0. Okay, next, inside is a little different. So inside the shell, total charge enclosed is going to be positive Q. So then we go 1 over 4 pi r squared Q over epsilon naught. And the direction that this is pointing, because it's positive, is going to be outwards. So the electric field is going to be pointing outwards in this case. Radially outwards. So what we would say is in the r hat direction. Okay, so total E field, we can usually write it like this: 0 outside, K Q over epsilon naught, r hat inside. All right. Next problem is number 53. This one's similar, but it's a little different. So here we actually have 2 shells, and we have the conducting material has some width. So the width of this is going to be, this is 2.4 meters, this is 2 meters. So this is conducting material in here. Okay, we have a charge that's negative 2 nanocoulombs in here. I'll write this in a different color. Negative 2 nanocoulombs here. This is 3 nanocoulombs here. Okay. Let's see, what else? What else do we need to know? We want to find the E field everywhere. So we want to find E field outside, E field inside, and E in the conducting material. Well, let's do this one first because that's the easiest. So for this one, E inside the conducting material is 0. E equals 0. Electric field equals 0 inside any conducting material. So that's something worth remembering. So inside the conductor itself, there is no E field. Okay, good. Now we want to do E outside. So this, we just use Gauss's law again. So we have 1 over 4 pi r squared times charge enclosed over epsilon naught. So that's going to equal, this is our K. Oops, this is our K. Where is it? Oh, it doesn't matter. Here, let's not worry about that right now. Just do this. Okay. Just double checking. KQ over R squared. So what did maybe I wrote that last one wrong. Sorry, I wrote this down wrong for the other problem. So it's kq over r squared, not kq over epsilon naught. Because k happens to be 4 pi epsilon naught. That's the value of the k that we're putting in here. So that's worth noting that I made a mistake here. So this is the correct answer. I just wrote it down wrong. Okay. So that means we have k, q enclosed, over r squared is going to be, let's do it down here, k over r squared, q enclosed for outside of this, well, the total charge enclosed in our Gaussian surface, this is a sphere, right, is going to be 3 nanocoulombs plus negative 2 nanocoulombs. So that gives us 1 nanocoulomb over k over r squared. So let's just write it down here. And then 1 times 10 to the negative 9 coulombs. So you can definitely plug that in. Let's see if I did that. Well, that's good. You can plug these into a calculator. If you have a value for r. So outside we actually took, let's see, what was it? There's a value for r somewhere. I'm looking for it. So the value for r outside is 2.5 meters. So then you plug in 2.5 squared here. And this ends up being, I think, 8 times 10 to the 9. And then it's like newtons, meters, coulombs per meter. Check the units on this. Oh, what did I have? It's in the book. So moving on. So just double check your answers here, and check your units. I forget right now the units of epsilon naught, but it's written in the book like several times. So okay, so now we want to do the E field inside. In here. Just double checking that I'm doing everything. Yep, negative 2 nanocoulombs. Okay, good. For this last one, just before we move on, the E outside. This is E outside. I should make this a little more clear. You have K, 1 nanocoulomb over, what is this? 2.5 meters squared. And this is going in the r hat direction because it's positive. So it's r hat, it's radially outwards. That's r hat. And then inside, this is going to be, because this is negative, this is going to be radially inwards. So it'll be negative r hat. So E inside is equal to K over, what was the value that we needed to go to? 1.5 meters. So it's going to be 1.5 meters squared, negative 2 nanocoulombs, r hat. Or you could write this K over 1.5 meters squared times 2 nanocoulombs, negative r hat, like that. You could write it either way. So total E field, trying not to be super sloppy here, but not sure if I'm getting that done. Okay, 1 times 10 to the negative 9 coulombs, r hat. This is outside. This is 0 inside, conducting material, which was the second value of r. And this one is 1.5 meters squared, 2 times 10 to the negative 9 coulombs, negative r hat. So that's the E field everywhere around that scenario.